Hello and welcome. This is a talk for the ICCV 2021 workshop on airborne object tracking. In this talk, I'm going to cover recent research that I was involved in, which is about segmenting and tracking every pixel densely in space and time. This work proposes a new task, a new data set, and evaluation benchmarks, as well as evaluation metrics for this task. It was a collaboration amongst many great collaborators, but the main driver of this work really was Mark Weber, and the corresponding paper of this work is going to be presented at the NeurIPS track on datasets and benchmarks this year, but the benchmarks are already available online, and in fact at this ICCV there is a first workshop on this work, on this new task. So what is STEP all about? Well, the task that we consider is also called video panoptic segmentation. The goal is to assign semantic classes and track identities to all pixels in a video. Here you can see a simple illustration of this. A state-of-the-art method might be a neural network that takes a video as an input and then has to segment and track densely in space and time all the pixels in that video. And it has to track all the trackable object pixels, for example, pedestrians and cars, and it has to segment all the other pixels. The contribution here is new benchmarks, in particular KITTI-STEP and MOTChallenge-STEP, as well as a new metric with what we believe are desirable properties for this task. Why does segmentation matter? Well, for autonomous driving, for example, it's of course important to precisely delineate the drivable area in front of the vehicle. It's also important to obtain a precise semantic understanding of the surroundings of the vehicle. And a pixel-precise instance understanding is in particular important in the context of other objects being close. Why does tracking matter? Well, of course, we have to anticipate the temporal evolution of objects in order to make predictions into the future and to determine the actions, to make a decision for the vehicle. In this case, in the case of autonomous driving, it's important also for obstacle avoidance and for motion planning, amongst others. So here you can see some examples of the annotations of our benchmark for a few consecutive frames in time. So it's desirable, I hope I was able to convince you that it's desirable to have such a holistic understanding where we really are able to segment and track every pixel, but at the moment we are lacking datasets for this task, at least datasets that are large scale and cover long periods in time, and that are not synthetic, but that really measure the performance of algorithms in the real world. We do have some data sets on related problems, for example on MOTS, which is multi-object tracking and segmentation, that covers already the problem of segmentation and tracking, but it requires the algorithms to segment only the trackable objects, as illustrated here on the KITTI-MOTS example. So it doesn't provide a dense segmentation. On the contrary, panoptic segmentation requires dense segmentation, but it doesn't have a notion of tracking. And therefore our goal is to define this new task, segmentation and tracking every pixel. And in particular, we're interested in tracking over long time periods. This task has previously been also called video panoptic segmentation. But what we provide here are new benchmarks and new metrics and a new perspective on this task. Let's have a look at the evolution of visual scene understanding over the years. We can separate tracking from recognition here. In the tracking branch here, we have the community has first considered rather simple problems such as single object tracking, and in recognition the detection and semantic scene segmentation. Towards autonomous driving, of course, it's important to track not only single objects, but multiple objects. And so single object tracking and detection has been combined into the task of multi-object tracking, for which now benchmarks are available. For example, the MOTChallenge and KITTI. And the object detection has also evolved in combination with semantic segmentation. The task of instance segmentation has been defined, where the goal is to not only detect objects in terms of bounding boxes, but really to delineate the exact pixel-accurate boundary. And a prominent example of a method that is addressing this task is mask-CNN. Now, more recently, the task of multi-object tracking and instance segmentation have been combined into the task of multi-object tracking and segmentation, where the goal is to track objects not only in terms of their 2D bounding box, but in terms of their pixel-accurate instance segmentation over time. But this, of course, only applies to objects that can be tracked, for which an instance can be derived. It doesn't apply to semantic categories like road or sky, etc. And simultaneously, the task of panoptic segmentation has been proposed that combines instance segmentation that is interested only in inferring results for the instance classes, like pedestrians and cars, etc., and the task of semantic segmentation in order to obtain a dense 2D segmentation of the image which encapsulates both the instances and also the semantic categories of the non-instance categories, like vegetation or sky. And now, at the very bottom is what we consider here panoptic video segmentation, or segmenting and tracking every pixel, where we want to have a full coverage both in space and time and a pixel-accurate annotation of both semantics and track IDs. So we want to track all the pixels that can be tracked, pixels of trackable objects, and we want to annotate all pixels with semantic labels. So here's a visualization of this, the evolution from tracking to step. This is the classical 2D bounding box multi-object tracking scenario, and this is what we attempt, a spatially, temporally, densely annotated scene. And for this we have new data sets with labels that are annotated densely in space and time for both the KITTI and the MOTChallenge dataset. Here's the visualization if you remove the background image, so you can appreciate the detail of the semantic and the instance segmentation. In summary, the contributions of this work are 2 datasets and benchmarks with held out data and evaluation servers called KITTI-STEP and MOTChallenge-STEP, which have been integrated into the KITTI and the MOTChallenge benchmark suites. Another contribution is a novel pixel-centric metric, STQ, which we'll talk about later, and some baselines to bootstrap these benchmarks to tackle both segmentation and tracking in order to address this task. So let's first talk about the datasets, KITTI-STEP and MOTChallenge-STEP. There are some existing datasets that we can build on and that also address this task, at least partially. KITTI-MOTS and MOTChallenge address the task of multi-object tracking and segmentation, but they don't provide dense coverage as discussed, so they are missing dense segmentation labels. Cityscape's VPS is one of the first real video panoptic segmentation tasks, and it provides indeed dense labels in space, but not in time. In this case, every clip has 6 annotated frames, and these are only every 5th frame that span only 1.8 seconds. So it's not dense in time, and it's also not long. It cannot evaluate algorithmic performance in terms of long-term tracking, which is important for self-driving, but it's hard. And then there is a number of synthetic datasets that can be used, of course, and for which it is very easy to obtain the required labels. But of course, there's still a large domain gap, and the photorealism is considered to be insufficient to date to transfer these results that we obtain on these datasets readily to real world driving, for example. Let's have a look at the annotation process for the STEP task. We base our 2 benchmarks on the KITTI-MOTS and the MOTChallenge dataset and labels for both the training and the test sets. For both of these, we have instance ground truth that's tracked over time. What we do is we first take every frame and annotate it semi-automatically using the DeepLab state-of-the-art segmentation, Panoptic segmentation algorithm to obtain a dense segmentation proposal. And this proposal is then iteratively corrected until the human annotators are happy with the per frame Panoptic segmentation result. And after multiple refinements by different annotators and a quality control process, the final result is merged with the instance ground truth over time from the KITTI-MOTS and the MOTChallenge dataset. And for these merged annotations, inconsistency in the instances are labeled as void because we can't make a precise statement about those, and so we don't want to penalize algorithms making a mistake in these areas. And second, ignored regions get the label of our human annotations. And this results in the final STEP datasets. Here's a comparison of the statistics of the KITTI-STEP and the MOTChallenge-STEP dataset here on the right to the Cityscapes video panoptic segmentation dataset. While Cityscapes VPS has more sequences annotated compared to KITTI and MOTChallenge, the sequences themselves are much longer for KITTI-STEP and MOTChallenge. And so overall, we still have more frames in this new dataset, about an order of magnitude more frames. And we have about the same number of semantic classes, for we consider less fine granular tracking class distinctions. Overall, we have about twice the number of annotated masks, but what's important is that we really annotate every single frame, not every 5th frame, like in the Cityscapes VPS dataset. And so this is the crucial aspect here, the crucial difference, that we can now not only evaluate performance of methods densely in time, but also over longer periods in time. As you can see here, for example, the mean track length in frames on the Cityscapes VPS dataset is 3, while on KITTI-STEP it's 51 and on MOTChallenge-STEP it's 187. So significantly longer than 3. Here's a comparison of the most salient classes in the newly proposed benchmarks. You can see that, for example, in KITTI, there is more vegetation, road, and building, while in MOTChallenge-STEP there is mostly sidewalk and building and pedestrians. Here's a comparison of the track length distribution. In the case of KITTI, we have pedestrians and cars as trackable objects, and in MOTChallenge we have pedestrians. And you can see that the track length there's some sequences or some scenes or some objects for which the track length exceeds 200 frames, and in the case of MOTChallenge-STEP, even 500 frames. So STEP really enables the evaluation of long-term tracking in the real world. So that's nice. Now we have a data set, but how should we evaluate? And this is where we propose a new metric, because we believe the current evaluation metrics are suboptimal. And this new metric we call STQ, Segmentation and Tracking Quality. Let's first ask, why do we actually need a new metric? The focus of benchmark papers is usually on the datasets and on the baselines, but not on new metrics. And there's only very few papers that indeed do a thorough analysis on the metric aspect. But it's really important to ask ourselves, what is a bad metric, for example? What is a good metric? What properties do we want? And can the metric be tricked? Is there a cheap solution to achieve a high score that actually doesn't correlate well with what human perception agrees on. Existing metrics such as the video Panoptic Quality proposed by Kim et al. And Panoptic Tracking Quality proposed by Hurtado et al. Build upon metrics for panoptic segmentation and multi-object tracking, basically combining those, but thereby, of course, also inheriting their drawbacks. And in order to develop a new metric, we came up with some properties, some desirable properties that we want to implement. And this slide compares these properties that are implemented by our STQ metric, as you can see here, to the prior metrics that have been used in the literature, PTQ and VPQ. For example, the first property that we want from such a metric is that we want to analyze full videos at the pixel level, not at the segment level. We want every pixel to matter in the evaluation. And this is something that STQ is able to do, but not PTQ. We also want to avoid thresholding. Often when comparing segmentations, there's a threshold. If you compare an instant segmentation, there's an IOU threshold. And if you're slightly above the threshold, then this is counted as a positive. And if it's below the threshold, it's not counted as a positive detection. And this is very brittle, of course, and depends a lot on the threshold choice. So we'd like to avoid this choice of the threshold. We also want to avoid penalties for ID recovery, or in other words, for correcting mistakes, for making something that's incorrect, correct. And it's quite surprising that some of these prior metrics actually penalize such mistake corrections, but that's not what we want. We also want the metric to take into account both precision and recall for the association problem, to balance the two, and to have a clean separation between segmentation and tracking errors, so that the metric decouples them. And this is something that is not fulfilled by the two prior metrics. So let's have a look at some examples and compare the result of the new metric STQ to the prior metrics. In this case here, the ground truth is two different object tracks that are following each other, while the prediction is one single track. All of these instances have been detected, they're correct, but they are detected as a single instance. The ID transfer has not been recognized. In this case, STQ is the only metric that properly penalizes the identity transfer. So we get a decrease in the score compared to PTQ, for example, by making such a mistake as misclassifying these two objects as a single. Here's another example where the ground truth is a single track, but then we have two predictions, one where we track for like one object for 2 frames and the other for 3 frames, and here one object for 1 frame and the other object for 4 frames. What we can see here is that STQ and also VPQ encourage long-term track consistency, which is what we want. In both cases, in contrast to PTQ, in both cases, the score increases, the tracking quality increases for the third case compared to the second case, which is what we want. The longer we can track an object, the better. Here's another example where the ground truth is a single track, and then there is one track where we have tracked this this sequence for 3 frames, but then have created another object here, and then there is one where we have tracked it only for 3 frames, but haven't even detected that. And in this case, only from all of these metrics, only STQ reduces the score when removing the semantically correct segment. So when going from 4 to 5, the score gets reduced. In contrast, in the other cases, the score gets increased, as you can see here. But our assumption is that, of course, for a self-driving vehicle, for example, it's better to detect an object at all, even though the instance ID has changed, rather than having it not detected, but having just detected one object for 3 frames over time. So we prefer solution 4 over solution 5 from a safety point of view. So let's look at the metric that we propose now. And let's start with a formal definition. The task of segmenting and tracking every pixel requires a function which maps every pixel xyt to a semantic class C and a track ID, which you call ID. And this is illustrated here. F of xyt, space and time, maps to the class and the ID. We denote the ground truth as gt of xyt and the prediction as pr of xyt. And our metric measures both the association quality and the segmentation quality separately to decouple the two problems, and then combines them using the geometric mean. Let's first have a look at the association quality. We define the prediction and the ground truth for a particular ID as follows. So for example, for the prediction of a particular track ID, we consider the set of all the pixels over space and time. This is a space-time tube of a space-time segmentation, if you will, where the prediction at xyt equals any class, in this case any trackable class actually only, and the ID corresponds to the ID that we seek. And the same for the ground truth. The proposed association quality metric, so we consider these sets of pixels because the proposed association quality is designed to work at a pixel level, therefore fulfilling the property 1 that we described earlier. And all associations have an influence on the score. So we're not considering any I or U threshold, as you will see later. We're considering it continuously. We are accumulating, we're integrating over all object hypotheses. And then semantic segmentation errors are not penalized in the metric that we propose. So we really decouple the two problems. They are only penalized in the semantic quality that we'll have a look at later. So this is really just about the tracking part of the metric. Okay, so let's see how this AQ is defined. We first define the true positive associations of a specific track ID, object ID, as the intersection of the predictions for ID P with the ground truth of ID G. And this is, again, the intersection over this space-time volume. Similarly, false negative associations and false positive associations can be defined like this in order to compute precision and recall. To account for the effect of both precision and recall, we define the basic building block IOU for this metric like this here. This is just a different way of writing the IOU. You could also write it in terms of TPA, for example, just to highlight that actually precision and recall both play a role in this metric. So now we have defined the true positive associations and the IOU. Following our goal of long-term track consistency, we encourage ID recovery, this is property 3, by weighing the score of each predicted tube by its TPA. So we are not just looking at the IOU, but we're weighing it by the true positive associations. And in the paper, we have some examples where we illustrate that indeed, by considering this weight, we are ensuring that ID recovery is encouraged. So the association quality metric is then the mean overall ground truth tracks, where we consider for each ground truth track the sum over all predictions that are not the ground truth, that are overlapping with the ground truth. And for this, we compute the TPA times the IOU, and we sum this all up. And this is our AQ score. The higher one tube, the best tube overlaps with the ground truth, the better this metric will be. And if this happens for all the ground truth tubes, will have a high score for AQ. The next part, the second part of the metric, is the segmentation quality SQ. For segmentation quality, we use the standard intersection over union criterion to measure segmentation quality. Formally, given the prediction at XYT and the ground truth at XYT and the class C, we define these sets here. And this is similar to before, but now we have fixed the class C and we consider all the track IDs here. That's why we have a star here, because this is about segmentation. And then we define the segmentation quality as the mean IOU, which is formally denoted here, 1 over the number of classes and the sum over the IOU for that particular class, where we consider, well, the IOU is simply the intersection over the union of the prediction with respect to the ground truth for that semantic class. Again, consider that this is over the entire space-time volume. Effectively, we're solving a segmentation problem in STEP over the space-time volume. Okay. Now we combine both scores into the segmentation and tracking quality STQ via the geometric mean. Very simple. Both can be assessed independently and they are combined in a very simple way. And therefore, STQ requires methods to perform well on both segmentation and tracking. Okay, so now we have defined the datasets, the benchmarks, and the metric. Now we need some baselines to bootstrap this benchmark. And we built upon the state-of-the-art Panoptic-DeepLab algorithm for panoptic segmentation. And this has been first introduced by Cheng et al., but we also propose a repository for a state-of-the-art implementation of this algorithm. So this is a state-of-the-art per-frame panoptic segmentation network, which has 3 branches. In the first branch, it predicts semantic segmentation. In the second branch, it predicts a center heat map. And in the third branch, pixel-to-center offsets, which can then be used to obtain the instance segmentations. And then these are combined into the final panoptic segmentation result. Now, this is only for single-frame panoptic segmentation. So how can we extend this to tracking? We consider 2 different approaches. Single-frame baselines, where we process this frame by frame here with the Panoptic-DeepLab panoptic segmentation baseline, and then we associate with very simple association mechanisms. And then we also consider a multi-frame baseline. So the first single frame baseline is using the panoptic segmentation results and associating over time using a simple IOU criterion, where the predicted Fing segments of 2 consecutive frames are matched by the Hungarian matching with a mask intersection over union threshold that's relatively low. To account for occluded objects, unmatched predictions are kept for 10 frames and can still be matched for up to 10 frames. As a second baseline, we use sort from Billy et al., which also does bipartite matching between sets of Kalman filtered track predictions and object detections. So it's using a filtering, a simple tracking mechanism in order to get better predictions into the next frame, and then considers the bounding box overlap. And then finally, we consider mask propagation, where we use a state-of-the-art optical flow method, RAFT, proposed by T et al., to warp each predicted mask at frame t-1 into the next frame, followed by intersection over union matching, similar to B1. As a multi-frame baseline, we propose center motion, which is adding a prediction head to the panoptic segmentation, to the DeepLab panoptic segmentation network, in order to regress every pixel to its instance center in the previous frame. This is inspired by Tractor and CenterTrack and other recent tracking methods. So this is a first baseline that considers multiple frames. How do these baselines perform on this new task? Let's look at the results on KITTI-STEP. So here are the four baselines, and we also consider VPS-NET, which is a state-of-the-art video panoptic segmentation algorithm. Surprisingly, the single frame methods perform better. At least there's one single frame method that performs consistently better than the multi-frame methods. The first column here indicates which of the methods utilizes optical flow, and both VPS-NET and mask propagation utilize optical flow. And we can see here in the first column the results with the STQ metric, and here in the back the VPQ and the PTQ metrics that we've discussed earlier. And here are the individual components of the STQ metric, the association quality and the segmentation quality. So we can see that single frame methods here in general perform better, even for the separate segmentation and tracking. And combining the state-of-the-art segmentation method, Panoptic-DeepLab, with a state-of-the-art tracking technique like optical flow, raft optical flow propagation yields the best results. So combining the best for individual segmentation and tracking, surprisingly maybe, yields the best results. So it seems like there's more work needed, and that's why we believe this dataset is very valuable to foster this research. There's more work needed to fully exploit the potential of multi-frame methods, which in theory, of course, should be better than this naive separation of the two problems. We're excited to see more work in this area. So here are some examples to demonstrate to you the quality of our labels, to appreciate the quality of the labels both for the KITTI-STEP dataset and in comparison here at the bottom the Cityscapes VPS dataset, where you can see here at 50% reduced speed that the sequences are much shorter and the annotations are less dense in time compared to the proposed dataset here at the top. Finally, let me point you to some resources. I've already mentioned that we are providing two challenges, the KITTI-STEP challenge and the MOTChallenge, where you can find the links here. You can try to beat the current baselines on these benchmarks and submit to the public leaderboards. We also provide a state-of-the-art DeepLab 2 implementation. And at ICCV 2021, we also host the first workshop on segmenting and tracking every point and pixel, which means that both of these challenges already have some contributions from third parties that are on the leaderboard. We're excited to see how we can increase the performance of these methods in the future. In summary, we presented a new perspective on the task of video panoptic segmentation, and we provided a new benchmark, STEP, focusing on measuring algorithm performance at the most detailed level possible, taking really each and every pixel into account. Our benchmark and metric are designed for evaluating algorithms in the real-world scenarios where understanding long-term tracking performance is important. And we believe that this work provides an important step towards a dense pixel-precise video understanding in the future. Thank you very much.